Good morning, all you cool mathematicians. Today, what we're going to be doing is going over how do we do exponents or powers of complex numbers. So you guys know how to do exponents when you just have I itself, right? That's what you guys know how to do. Um, and that's not too bad. We just divide that by 4, see how many times it spins around the circle, and so on. But what if we don't have just something that is, just I to a power? What if it's a full complex number to an exponent, right? I mean, that would take a long time to go. So we're going to see how do we kind of speed that process up and how do we go through that today. So our kind of initial thing to look at is, we're going to look at things in trig form because it's a lot easier to do exponents when things are in trig form. So in here, if I have, say 2 cis 30, again, that's at a radius of 2, and then we've turned 30 degrees up. You kind of look at that one, and now we're going to the 4th power. What we can do, again, exponents just mean repeated multiplication. So in here, what we can go through is we could say, well, really, that's 2 cis 30, and then times, well, this part again, right? I mean, it's times this, times itself again, and there's 4 times. That's what that is. It's that 4 times over. And well, that can be a little tough, but we can always rearrange this a little bit. We know from multiplying complex numbers together, as long as they're in trig form, we can kind of easily do that. We can just multiply these magnitudes or these radii out in front. We can multiply all those r values together, which in this case is just 2 times itself 4 times over. Right, and then there's that cis. And well, and here we would do, when we're multiplying complex numbers, we add their angles together. It's kind of like a rotation. So here it would be 30 plus 30 plus 30 plus 30, right? That's really what that is. Now we can simplify this a little bit. I understand, yeah, we could type in 2 times 2 times 2 and get the answer, but I want to look at the process here. So when we multiply all these together, this is multiplying 2 4 times over, so that's really 2 to the 4th power. And when we're repeated addition in here, repeated addition doesn't become an exponent, that's a multiplier. So this is like 4 times 30, correct? So we can kind of take this whole huge process here and we can simplify it down. We've rearranged it, but if we look here, this same radius, right, this number has been multiplied 4 times over. So whatever the exponent here is should be the same as the exponent here. And this angle in here will get added however many times over. In this case, we're adding 30 4 times over. And so that's the same as doing 4 times 30. It becomes a multiplier on the inside. And that's the whole thing, right? That is the whole process that we're going to kind of take a look at. Excuse me, that we're going to take a look at today. And what that's called, this kind of theorem was discovered by a particular mathematician named Moivre, if I'm pronouncing that right. I always kind of pronounce it a little differently. If you want to see how to pronounce it, you can follow this link, and it will, show you how to, or tell you, you can listen and see how to pronounce that. Or sometimes you can just call it the DMT as well. But how de Moivre's theorem works on here is it's kind of that same process of what we were looking at, right? On here, we can just say, oh yeah, if this is r cis, our radius, here's our angle. Really what that's going to be is we just take r to whatever that exponent is, because that's going to get repeatedly multiplied, and then the angle on the inside is going to be added repeatedly. So in here we can just say, well, all right, that's just going to be n times, see if we can put that in there, times our angle, right, whatever that is. And that is what that theorem is. That's all there is to it. Not too much more. Now there are some slight variations if we do fractional powers, which we'll go over in just a second. But it's, other than that, that's the whole thing. There's nothing much more to it. So we'll do a couple examples on here just to show you what I mean. So here's one example I put. We have a radius of 8 and it's turned at an angle of 65, right? So it's 8 away, turned at that angle of 65, meaning it's in quadrant 1. So in here, again, let's grab this whole thing so I don't have to retype it all. But in here, we would just take our 8 to the 3rd power, and then we'd take 65 times 3. So in this case here, it should be 8 to the 3rd power, and then, oops, let's get out of that exponent, 65 times type while I'm not talking. Sometimes I can do that correctly. And then, so we just do that. And I just grab my calculator. I don't know what 8 to the 3rd is off the top of my head, so I'd have to do that. Ooh, if I can type it in there. So that's 512. And then we would say sys whatever 65 times 3 is, which is 195, right? I mean, there's that result. That's what we would do in that case if we wanted to do this example, right? And now if we want to put that back into what's called our standard form, again, this is trig form, right? If we want to put it back into standard form, again, this is cosine I sine. So if I want to put this back into regular form, let's just get rid of all that. What we would do is we do 512 times the cosine of, our 195 plus 512 times the sine of 195. And the sine, since that's a vertical component, that'll just be our I value. And then there we can just type that into our calculator to see what that is. So I do 512 times cosine of 195, which is, not a nice, number. I got to round it a little bit, 0.55. Plus, well, then we do the sine portion in here. So let's do 512 sine of 195. And okay, that's negative, so I'm going to change it to subtract 132.52. Always rounding to a couple decimal places. I better put my I in there. So that's if we want to take that all the way to standard form, which, in your assignments, you'll have to do a couple things where it's easy to do de Moivre's theorem, and then to get it to standard form, multiply times cosine, multiply times sine. And there you go, right? Or, a lot of the stuff in your homework is going to work out perfectly to be like 30, 60, 90 triangles or 45, 45, 90 triangles. So you can just leave the square roots in there as well. That's perfectly fine. So that's where we've got it in trig form. We take that one through, not too bad on there. Our next example here is, again, this part to the 5th power. It is a complex number, and we're going to need to take that to the 5th power in this case. So it's a lot easier to do, multiplying and in turn exponents when things are in trig form. So I need to change this one to trig form. So here I would just kind of think about, or maybe draw on our map or on our grid where this thing is. So it's about at 2 times root 3, which square root of 3, and about 3.4. And it's somewhere out here, right? 3.4-ish, and then down 2. So it's somewhere over in here, correct? That's where that number is located. It's over that amount and then down. And then in here, we could kind of connect this stuff up, right? I can make my right triangle. If I'm going to put this into trig form, I kind of have to do that. And what I can figure out on here is actually, by doing the Pythagorean theorem, we would find that this side is 4, right? We would do that and say, oh, that's a 30, 60, 90 right triangle. Or if you weren't sure, you'd always use your calculator and do like the inverse tangent or something like that to find that this angle in here is actually a 30-degree angle. So I know that the full way around is 330 degrees this way, right? Our reference angle is 30. So that means in standard form, it's 330 degrees. And in fact, it's got to be 4 away. So I know in trig form that this is 4 cis 330. I'm going to put that 0 in there. That's the same thing. And then we're going to raise this to the 5th power, right? That's what that one is. So very simply, we would do 4 to the 5th power, and then we do cis of 330 times 5. That's what we would do there. And our 330 times 5, we would get that. We would do 4 to the 5th power, and then we just write those 2 things in here. So, times 5. We get on the outside of that. Doesn't want to be nice to me, so we're just going to say, all right, fine. Let's put that in there. Okay, and then we type that stuff in our calculator. 4 to the 5th is 1,024. 330 times 5 is, what I got, 1,650. And I'm going to put back my, I haven't been doing this. Normally, I guess I haven't labeled it as degrees, but just so we know that this is a degree measure, and there I'm going to re-emphasize that at this point. And now here, we would think we're done. We're not quite done yet, right? If I want to keep this in a nice form, we usually want that angle in between 0 and 360. So what I'd have to do is I'm just going to take 1,650 and keep repeatedly subtracting 360 from it until it drops to something in between 0 and 360. So if you repeatedly subtract 360 from this number, you'll eventually get to 210 degrees, right? So that would be in there also. So that, there's our trig form of it. You can change that back to standard form. You can multiply times cosine of 210 times sine of 210. Or another way you could do that too is actually 210 degrees is 30 degrees more than 180. So you can think, oh, hey, wait, that's a 30, 60, 90 triangle. We know that the radius is 1,024. So that would mean this side's half of that. So if you wanted to, you could use your knowledge of 30, 60, 90 right triangles to say, oh, the radius or the hypotenuse is 1024. That means, well, that short side, the up and down part is, 500. Let's just make sure I'm not at 512. Okay, I was right on that. And that's the up and down part, 512. And that means the length has to be 512 times the square root of 3, right? I mean, using just our knowledge of 30, 60, 90 triangles, we could know that would have to be true as well. I know that's not necessarily showing up on the video here, but it'll show up in your notes. So you can do that too, or you could type it in your calculator as well. Do 1024 times the sine of 210, and you'll get 512. In fact, negative 512, because it will be below the axis in that third quadrant. So this would be in standard form. This would be leaving it in trig form. Yeah, so that's the main stuff with de Moivre's theorem. At least when you have nice numbers, we take it here, and then we multiply it. So to get a little more into refinement, the last thing we're going to go into for today is what if we want to do roots of numbers, right? Or in other words, like square roots, cube roots, fourth roots, things like that. The thing to keep in mind is that roots are fractional powers. And the other piece that we need to keep in mind as well is that anytime you take a root, you should get multiple answers, right? That's actually the one of the fundamental theorems of algebra, is that whatever the exponent is, that's how many answers you should get, right? We should have that many, which you guys kind of know intuitively. We might remember, like, hey, if I need to solve this, most of the time we could say x equals 4, or possibly, right, this could be -4, right? It's squared. We could get 2 possible answers. It makes sense, right? But one that we don't really talk about too much outside of trig is like cube roots. I mean, if that theorem was true, this should really have 3 answers to it. And we know one of them, right? We'd take the cube root of 8. And you guys would say, sure, x equals 2. That does work, right? 2 times 2 times 2 is 8. That's one of the possible. But there should be 2 others, right? What are the other 2 ones? Correct? Because it's a cubed power, there should be 3 total answers. And the thing is that until this point, until you're really taking some in-depth trigonometry, you don't have enough knowledge to really understand what these 2 extra answers are. So we sort of just say, let's just do this one, right? We'll stay just in the real numbers because these are going to be complex answers. And it may seem like it's going to be a little complicated to get those, but it's actually not too bad. So here's our steps to do that, and then I'll put a few examples down as well on how to do those. So to use the DMT, or de Moivre's theorem, to solve this, the first step we have to do is to write the result in trig form. So in here, I wouldn't write x cubed equals 8. I'm going to write x cubed equals, well, 8. Well, that'd be going out 8 just along the axis, and I wouldn't have turned any. There would be no degree measure to it, kind of. It's actually 0 degrees, right? It hasn't moved at all off the axis. So this would be 8 cis 0, right? I mean, that's all that that is. I'll make sure it's defined as 0 degrees. So that's our first thing, right? We write that in trig form and then also take the third power. If it's a 3 over here, we would solve that by, instead of doing 3 here, we would do the 1/3 power over here. Right, and so that's what I'm going to put in there. And then we would solve that, right? And so we can put that in a trig form and we can solve it. And then here we would use the Moivre's theorem to go about this, right? We would say, well, all right, this means this is 8 to the 1/3 power. That's what that is. And then 0 divided by 3, or 0 times 1/3, which, 8 to the 1/3 power. Let's actually just put all this all the way back in. 8 to the 1/3 power, and then times cis of 0 times 1/3. I'm going to write it like that. If you want to think about it like dividing by 3, which I'll do in the other examples as well, I just want to emphasize that we're multiplying by a fraction. That's the same thing as dividing. Well, this should be equal to, well, 8 to the 1/3 is 2, right? And then that's cis of 0, right? Because 0 times 1/3 is still 0. So, I mean, in that case, we don't have anything exciting. It's 2 cis 0, which is exactly the same as 2, right? Because that just means it's on the x-axis, the real axis, just over 2 and don't move. So you got 2 plus 0i. You don't move up or down at all. So this gives us the same thing. It's like, oh, great. But where are the other 2 at? And this is the third step. And that's to move around the circle. What actually happens, and this is the crux of de Moivre's theorem, is that this first part of de Moivre's theorem gives us one result, but there are multiple results going around the circle. And how we find those multiple results is we have to take the whole circle and divide by whatever the exponent was. In this case, we're going to divide by 3. So in this case, we would say, well, that's 120. So we have to jump around the circle by 120 degrees. Yeah, degrees, right? So what that would mean is we take this trig form and we continue to move around. So we're at 0 degrees. The next answer is going to be 120 more degrees than that, and then 120 more degrees than that. And then if we do 120 more, we're all the way back around at 360, or the same as 0, right? So the solutions to this, right, the solutions to this thing, how we would get them, we would say, well, it's going to be 2 cis 0, right? That's one possibility. And it's not going to let me do enter here, is it? Nope. Doesn't like me to do that. All right, so there's one possibility in there, right? And then our next possibility would be 0 plus 120, right? That's our next possibility. And then the next possibility would be plus 120 again, or plus 240, right? So those are 3 things, because if we add 120 again, that's going to get us right back to 0, because that will have completed a full circle. So the 3 answers in there are 2 cis 0, right? Let's actually put this in here. 2 cis 0. And then the next one is going to be 2 cis 120. And then the last one is going to be 2 cis 240. Okay, so there are our, there we go. Okay. So we should have those ones there, or maybe I'll come back and reformat these so it looks really nice. So those are the 3 possible answers in there, right? So we're just moving around the circle by, whatever portion we are of 360. Okay? So I get that that's a lot of information there. I'm going to do a couple more examples. If it's making sense to you and you want to jump to the homework, you can. Or if you want to I'm going to take a brain break, come back to this, you certainly can. But I'm just going to go through 2 more examples to show you fully how that works. So we're going to go in here. This is one we're going to solve. X to the 5th plus 32i equals 0. So our first part here is we have to solve for the x variable as much as possible. Let's see if we can get this guy working. Okay. So we'd have to solve for x, so that'd be x to the 5th is equal to negative 32i, right? And that's what we'd have here. Nope, I lost track of it. And then our second step there is to write, or our first step, I guess, still from that one, is to put this into trig form. So I know negative 32i is to go down 32. So that would mean we have a 270-degree angle to get there, and we move down 32. So really, this is x to the 5th equals, in this case, we would have 32 cis 270, right? That's what we have there. So that's our start to it, right? That's what we'd have to start there. And then what I would do after that point, I would say, okay, well, we need to take this to the 1/5 power. So I'd have 32 to the 1/5 power. And then we'd have our cis cosine I sine 270 divided by 5, right? That's what we would get there, which we could work that out. Again, I would, maybe grab my calculator. 32 to the 1/5, you could type that in. I know that that's 2 because I've been working with this for a little bit. I've been doing these a little bit ahead of time. But 270 divided by 5, I don't remember what that is off the top of my head. Okay, it's 54. Cool, so we'll put 54. That's the first answer. This gives us the first initial result, right? This gives us our first initial result. So to get the other results, right, all the answers, how we get all the answers is I first start with this one, 2 cis of 540. Okay, that's what I would start with. And then what I'm going to do is I'm going to take my calculator and I'm going to say, well, it needs to have 5 possible answers. That's the first one. So I need to take 360 divided by 5. And so I need to keep turning. 360 divided by 5 is 72. I need to keep turning by 72 degrees. So my first one would be 54 plus 72. So I would have 126. Okay, put that one in there. And then I would add 72 again. That's 198. Put that one in. And then I would add 72 again. 270 degrees. I'd add it again. That's 342. And then I would add this one last time. And that's at 414, which actually is the same as a 54-degree angle. So that would be the last one in there. Must have forgotten to put one in there. Huh? 271. I must have forgot to hit that. Right. So there are all the possible answers. And I should probably put our original one of 54 because that's the same as our 414 if we went around. So let's grab all of those and we'll just put these on this page, right? And so we'll put these in a nice little order so that we can kind of see, oh yeah, we're just adding that each time, right? All answers we need to start or turn by, in other words, add. Let's see, how did we figure that one out? We did 360 divided by 5, which is 72. We're going to turn by 72 degrees each time, right? In other words, we're going to add 72 to the angle 5 times, or actually, well, just 4, because we don't, by the 5th time, it'll circle back to the first one. And that's how you get all those answers. And we're just going to leave those in trig form. If we wanted them in standard form, I could do this one, 2 times cosine of 54 and 2 times sine of 54. That would give me the standard form of that one. Yeah, nothing too major on there. All right, last thing here, just again, to see that example or see that stuff work through if you need another one, we're going to solve here x to the 6th, this part. All right, equals 4 minus 4i. So I think of where that one's at. It's going to be easier in trig form. So I'm going to first start x to the 6th. I'd want to solve it first, right? This is 4 minus 4i, right? That's what that is. However, that might be a little bit easier to put in trig form to use the DMT. So I think, okay, I'm over 4 and then -4, right? Forward 4 and then down -4. So that's got to give me a 45-degree angle, but it's in quadrant 4. So I want to update that as nicely as possible. So the radius here would have to be 4 squared, 4 squared, go around. It's a 45, 45, 90 right triangle. So I know the hypotenuse is 4 times root 2. I know the angle has to be 315 degrees because it's 45 short of 360, right? That's what that has to be in trig form. And then to fully solve this here, what we're going to do is take this to the 1/6 power, right? To the 1/6 power. Alrighty, so that's what we're going to do here. So now you can go ahead and use your calculator. You could do 4 times the square root of 2 to the 1/6 power if you want to do that, and you'll get a big long decimal answer. Maybe your calculator will have enough to keep that in radical form, and I'll show you that in just a minute how we can do that. But here, this part, that's what I want to concentrate on first. Yeah. So our 4, we'll leave this in a second. We'll say, okay, what we really should do is take this part, let's go out of here, to the 1/6 power, and then 315 divided by 6, right? That's what we're going to do in that case. And so what we would do here, I'm going to leave this part for just a second, but now we would put all our answers. So of which there's going to be 6 possible answers this time, 6 answers. All right, so we need to turn by, in this case, we're going to need to turn by 360. So let's just get rid of this for a second. We're going to need to turn by 360 divided by 6, which is equal to 60 degrees. So we're just going to take whatever that number is, whatever that angle is, and we're just going to keep adding 60 degrees until it gets all the way around in there. Okay, so in this case, I'm going to take out this x equals and get rid of extra exponent. So here I would take, all right, 315 divided by 6. Now 52.5, which is just fine, right? 52.5. Maybe we don't need these extra things out here. Take those out. So that's our first one. And then what we would do is just take our answer and keep adding 60 degrees to it. So I'd take that plus 60, so we'd get 112.5. There's one of them. Add 60, oops. Add 60 again, get 172.5. Not bad. I get, probably don't need a calculator to go here, but you know, I'm just gonna make sure, because my calculator, I can just put plus answer plus 60 and then just keep hitting enter. And you know, if you have a calculator like that, you can just keep generating all of the answers. So 232, 292, 250, or oops, 352.5, and then if I add 60 again, it's going to go past 360 to 412.5, which is the same as that spot. Then we can stop there. So there's all 6 of them. One of them I must have forgotten to type in, and I'll go back and find that one. I must have forgotten to put it in here. So I'll find that and put that one in there so it's there for you in the notes. But that's the whole thing. Now you can leave it like this. You know, that's fine. If you want to simplify this for 2 to the 1/6 power, that's what I'll go over here next. If you don't want to watch that and you just want to jump into the homework, you certainly can. But here, a way to work this out is to see that, okay, 4 is actually 2 squared. This 2 is to the 1/2 power, so I'm going to say 4 is 2 squared. The square root of 2 is 2 to the 1/2 power. And then we have this big 1/6 power on the outside of that. And so what we would do in this case is we could add these exponents together, 2 plus 1/2. And I'm going to keep it in fractional form, so really this is 2 to the 5/2 power, right? That's 2.5. We add those together, and then, oops, to the 1/6 power in there. Now, when we do fractional powers, we take, or when we do powers to powers, we multiply those powers together. So really, we could say that this is 2 to the 5/12 power if we wanted to do that. So if you wanted to simplify that number in front, I know this kind of expands a little bit. Maybe we'll just make a new thing there. You know, you can put this, you could put the 12th root of 2 to the 5th, or you could even say like the 12th root of 32, right? That's what that would be. I can't quite get it to make 12th roots in this little program, so I'm not going to put that in there. But you could put that. You could put the 12th root of 32 if you don't want to keep rewriting this front part. But if you leave it like this, then fine, right? That's okay. The main part is knowing, okay, we've got to keep adding 60, which, you know, I'm missing 1, 2, 3. I'm missing one of them in here. Yeah, and I'll find that one and put that one back in there. But that's kind of the whole thing. I'm all the way around. I'm missing that one in here. And so that's how you use de Moivre's theorem. I know this one's a little bit longer, but I wanted to make sure, you know, you guys have some examples that if you want to look back at those, you can. But if you have any other questions too, make sure, you know, send me an email, something like that. I can always make more videos kind of explaining that, or put up some pictures of how to set those things up if you guys need. But otherwise, good luck.